uncertainties in our design. Aside from the specifications required of us, our team had a few key goals in mind during the design process. With the target of a high position in the UCL competition, it has been necessary for us to ensure the utmost quality and accuracy at each step. We wish to complete this challenge well below the time limit, minimize costs and uncertainties in our design wherever possible, all while using original and creative concepts.
Aware of the size and cost limits, and most crucially the need for our vehicle to operate entirely mechanically, our team ensured that we followed an iterative design process, brainstorming ideas together and discussing the benefits and drawbacks of each concept. We created sketches to visualize our components and conducted research into existing similar modules to see what will work and what will not. In order to measure distance mechanically, our team decided that the best way forward was a component that tracked a physical distance, as opposed to relying on energy conservation, as this would likely lead to greater uncertainties. Our clock mechanism functions through the rotation of a swirl connected to the motors, forcing a pin to move up a rail. This pin would track the distance covered in the swirl, and upon the vehicle reversing, the swirl would rotate in the opposite direction, causing the pin to return to its original position where it would activate the stop switch.
We initially attempted to make our own gear system comprised of multiple compound gears to achieve an effective gear ratio of 1 to 256. However, a brief cost analysis showed us that this would be unviable, as the motor and all the gears with particular diameters and thicknesses would have to be individually ordered, in addition to suitable rods to keep the gears in place, massively increasing costs. Therefore, we decided to order a pre-built, mass-produced multi-ratio gearbox and replicated it on Fusion 360 to implement to our finalized model.
After exploring various initial concepts, we decided to choose a continuous track design for the forward movement. This will allow for better alignment due to greater surface area in the contact with the ground, which will decrease the likelihood of deviation in the horizontal direction. With this design, we can guarantee that the front and the back wheels will rotate at the same amount, which is necessary for the clock. Additionally, each link of the track has a piece of rubber embedded, allowing for better grip and thus decreasing the chances of slipping when decelerating.
Our final concept for reversing the direction of movement depends on inverting the polarity of the motor. This system involves a push bar, which, upon hitting the wall, will rotate a gear, causing a lever, i.e. a trigger, to lift, releasing a block connected to a spring in compression to a known rest position as shown on the left. The block will contain two wires positioned such that the circuit current will be reversed when placed in the new position. This system will be reset each time, i.e. the wire block will be pushed back to its original position. Having finalized all the key components, we assembled our vehicle in a singular file. We applied physical materials and added extra features to combine each component, such as axles and a base, as well as the case to hold the batteries. Our team prides itself on our original approach to the problems proposed, drawing particular attention to the unique designs of the tracks, clock, and reverse mechanism.
In order to proceed with the calculations, we had to consider the total mass of the vehicle. We used Fusion 360 to determine the mass of all the components except the 3D printed ones. For those, we used Ultimaker Cura to compute the mass of every 3D component with a 20% infill.
To create a mathematical model for the motion of our vehicle, we had to take some assumptions about the unknown values. These unknown values are listed in the slide. We performed research and determined reasonable assumptions for these values. As an example, we found that the efficiency of a spur gear is not lower than 98%. Therefore, we considered the losses due to friction in the spur gears to be negligible. Using the mass of our vehicle, the gear ratio, the stall torque, and the no-load velocity of the motor, and the dimension of the wheels, we built a mathematical model to show the motion of the vehicle over time. In the graphs are a few key. In the chart is a few key details, and two sets of graphs, which represent the motion of the vehicle over time: the position, velocity, and acceleration. The graphs on the left represent the motion of the vehicle from the start of the race to the point when the vehicle becomes steady. The graphs on the right are applicable for the moment when deceleration begins at the wall, beyond the point when the vehicle changes direction. Thank you for watching.